Humanity first set foot on the moon in 1969, and then the silence began. For more than half a century, no human traveled beyond low Earth orbit. The moon remained distant, untouched, observed but never visited. Now that silence is about to end. Artemis II marks humanity's return to deep space, the first crewed mission to travel toward the moon since Apollo. But this mission is not about landing. It is about something far more critical: coming back alive. On board Artemis II, there are 4 astronauts, 4 humans traveling farther from Earth than any human has in over 50 years. For nearly 10 days, they will live inside a small metal spacecraft. No fresh air, no water supply, no rescue. Every breath, every sip of water, every meal has been calculated long before launch. And in this documentary, we ask a simple question: what does it really cost to send humans to the moon? Let's begin with the mission itself. After launch, the spacecraft enters low Earth orbit. Then comes a critical maneuver, a powerful acceleration known as translunar injection. This is the moment when the spacecraft escapes Earth's gravity and commits to the moon. As Orion approaches its destination, it will pass behind the moon, over the far side, a place invisible from Earth, a view no human has seen since Apollo. The moon's gravity will then act like a cosmic slingshot, redirecting the spacecraft back toward Earth. This is known as a free return trajectory. Even if engines fail, physics itself brings the crew home. This path was chosen for one reason: survival. Now we arrive at the heaviest part of the mission: fuel. The greatest mass aboard Artemis II is not the astronauts, it is fuel. Approximately 2.6 million kilograms of it. Yes, millions. More than 90% of that fuel is burned within the first 8 to 9 minutes after launch. Because the hardest part of spaceflight is not staying in space, it is leaving Earth. Rockets must lift not only their payload, but also the fuel required to lift the fuel. This creates a brutal equation. To move a little more mass, you need exponentially more energy. That is why the oxygen used by 4 astronauts over 10 days, just 36 kilograms, is almost meaningless compared to rocket fuel. A single rocket engine consumes more than that in seconds. So let's talk about breathing. In space, air is engineered. Inside the Orion capsule, the atmosphere is carefully controlled. Oxygen is present, but not pure. Pressure is lower than on Earth to reduce fire risk. Each astronaut consumes about 0.9 kilograms of oxygen per day. 4 astronauts, 10 days. That's roughly 36 kilograms of oxygen. But oxygen alone is not enough. Carbon dioxide must be removed, humidity controlled, pressure constantly monitored. If a leak occurs, sections of the spacecraft can be sealed. Masks deploy instantly. In deep space, a single failure can become fatal within seconds. Now consider water. Water is the most precious resource in space. It is needed not only for drinking, but for food preparation, hygiene, and life support systems. Each astronaut uses about 4 liters of water per day. Across the mission, that totals roughly 160 kilograms of water. But water is not simply consumed. Much of it is recycled. Moisture from breath, sweat, and condensation is captured, filtered, and reused. In space, water is not wasted. It is preserved. Because on the moon and beyond, water means survival. And then there is food. Food in space is not just nutrition, it is morale. Each astronaut requires about 2 kilograms of food per day, including packaging. Over 10 days, that becomes roughly 80 kilograms. Space food must not crumble, must not release gas, must last for months, but it must also feel familiar, because isolation, monotony, and confinement are among the greatest challenges astronauts face. In space, hunger is rarely the enemy, repetition is. There is one system few people like to discuss: waste. 4 humans, 10 days, a sealed spacecraft. Everything is managed. Solid waste is compacted. Liquid waste is processed. Bacteria are controlled. Odors, gases, and contamination are monitored continuously. Spaceflight is not only about propulsion, it is about sustaining life in isolation. Now we reach the unavoidable question, cost. The total estimated cost of Artemis II is approximately $4.1 billion US, around $2.2 billion for the Space Launch System rocket, about $1 billion for the Orion spacecraft. The rest goes into testing, safety systems, mission control, and years of preparation. Why so expensive? Because human spaceflight demands near-zero failure. Every bolt, every wire, every line of code is tested again and again. Many systems are used only once, but when human lives are involved, there is no acceptable shortcut. Now step back and look at the numbers. 4 humans, 10 days, 36 kilograms of oxygen, 160 kilograms of water, 80 kilograms of food, all supported by 2.6 million kilograms of fuel. The contrast tells a powerful story. Sending humans to space is not limited by biology. It is limited by energy. Artemis II will not land on the moon, but it will decide the future, because before humanity can build lunar bases or travel to Mars, one question must be answered. Can humans survive deep space? And just as important, can they return safely? Artemis II is not the destination, it is the test, and what follows next will demand even more. If you want to continue this journey, the next chapter is Artemis III, the mission that aims not just to fly past the moon, but to land. And when that happens, the cost and the risk will rise even higher.